Все идет, Паша? Паша, пошло или нет?
Ну да, ссылка появилась. Я сейчас проверю, что там все нормально, но вроде бы все нормально.
Хорошо. Давайте я сейчас еще планшетки готовлю, а потом их. Еще пару минут, давайте подождем.
Скажите, а там какое-то название лекции написать или просто лекция 1?
Нет, просто лекция 1, лекция 2 и так далее. Спасибо. Я потом у вас научусь как-то самому делать, чтобы вас не напрягать ранним вставанием. Ну, хорошо, мы начнем. Okay, it seems that we have at least one non-Russian speaker, so we'll switch to English. Before we start our first lecture for the course, I would like to ask you, first of all, just to turn, at least for a short period of time, your video on. I would like to see faces. Usually seeing faces is an important part of interaction with students. I'm not expecting you to be alert all the time, so just after some time you can switch on your video, but to begin with, I would like to see you all. By the way, do you hear me? Is it okay? Okay. Okay, this is a very unusual structure by meeting this course. And there is no way directly, at least for some time, to communicate with you. So if you have some questions, you may ask them during, and I would like you to ask questions during the lecture. But if you want to discuss something, I'll set a meeting time for so-called, how it's called in the Western University, for office hours. I will be available, say, on Mondays from 10 to 11. And if you send me that you want to meet during that time, we can meet. I'll provide later the Zoom link for these office hours. I'll schedule them. And also, I would like to ask all of you to send an email with your name, affiliation, just to have an idea. There is no need for official registration for this course, but just to know who's attending, what is your background, so you're a student or something. Just send me email. My address can be found. I'll write it later, probably. All right. Right now, I'll start sharing my screen. So the email is Krichever at Mass Columbia U. Sometimes this address sends a message that it is not delivered. Don't pay attention, it works. But somehow the Columbia server doesn't like mails coming from Russia sometimes and put it and indicate that it's going to for spam, but it's not the case. Okay, so just use this email to send me a message so I can compose a list of students for some announcement if they come. Okay. This is all. Once again, there will be office hour on Mondays starting from 10 to 11, in which you can almost privately meet and discuss your questions if you have them. Okay. Any questions regarding the course? Not yet. Okay, then we can start. Today is just introductory lecture. I would like to explain what is going to be in the course on integrable systems. Official title is Classical Integrable Systems. I put integrable systems because now it's a mixture. Sometimes some quantum integrable systems are, so their solutions are expressed in terms of classical integrable systems. So there is no particular need to specify classical or quantum, but it's going to be a course about basics of the theory of integrable systems. I put a list to begin with of some basic examples of equations that are considered in the framework of the theory of soliton equations. The list starts with the famous equation called Krichever degrees, and it was the equation which was the first discovered to be integrable. Then it goes nonlinear Schrödinger equation, Sine-Gordon equation, Toda lattice, Calogero-Moser system. There are actually three types of this Calogero-Moser system with the potential. So this expression here is just v prime of xi minus xj. V is a function in such a way there should be probably two here. The particular form of these equations are not so important for us, and we will touch very little the nature of this equation, how they came from physics, what type of systems they describe. For us, the most important, the focus of the course would be of some structures behind all this equation, how one might think about them, what is the picture behind so diverse equation. At first glance, they all look quite different. So what unifies them? What is the structure that actually came to life when people tried to solve this equation? Each of the equations came from some physics model, and surprisingly, it is possible to solve them. What solution means, let's not talk at this moment. Just you can solve them, although it's non-linear equation, and a priori there is no way to treat such equation but just using a computer. But it turns out that they are solvable. And I'm not going to present, there is no universal view on how to define such an equation. I present my view on it, mostly algebraic geometrical understanding of structures of integrable systems. For others, experts, they will say that integrable systems are tau function, forget what it is, or this is R matrix. So there are different views on what is called integrable systems. Again, the way how I see it and how I would like to present it have a flavor to some extent similar to what first come to your mind when you hear the word Hamiltonian system? Okay, there are tons of Hamiltonian systems, but what if you want very briefly to introduce the notion of Hamiltonian system? So what is Hamiltonian system? Hamiltonian systems, if you want to be very universal, is nothing but the manifold with symplectic structure on it. Having manifold and symplectic structure and the function, you define a vector field, and that is your Hamiltonian system. So I would like to have something like that for a theory of integrable systems. I would like, at the end of the day, to present a self-consistent way of thinking about the integrable system, forgetting about very different nature of these equations. So the list continues to the Hitchin system. Probably we'll come to them later. I'll explain each of these equations, maybe in more detail, but again, the particular way of looking at their origin is not important. I would like to unify them in some picture similar to what I said, how I think in two words about Hamiltonian systems. So this is my goal. And the goal for these lectures, just to give you a description of our course. So what is going on? What it will be in this course? So we'll come first to the definition of this system. And rough classification, if you call it classification of integrable system, is 0 plus 1, 1 plus 1, 2 plus 1. What that means? That means the following. So what is equation? How, this is the first point I would like to say. So we think, like in the Hamiltonian mechanics, when you have a function called Hamiltonian, you have a symplectic form. That pair defines a vector field, dH, which is defined as a vector field whose contraction, so you substitute this vector field into the symplectic form. Symplectic form is closed in symmetric non-degenerate to form. So if contracted with the vector field, so you just put it as one argument, you get one form, and this one form should be the differential of your function. And then having a vector field, you think about your system as a dynamical system. So dynamical system is a vector field with trajectory. So having a point, you move along a vector field. This is your Hamiltonian system. Similarly, we will deal often an example. I will stay mostly within the theory of finite dimensional system. And finite dimensional systems are systems called 0 plus 1. 0, 1, and 2 staying in these brackets is just functional dimension of our space. So 0 means it's a finite dimensional space. One dimensional, 1 plus 1, so 1 is a time, and then this is functional dimension. So 0 plus 1 systems, so finite dimensional systems in the list I gave here, it is 4, 5, and 6. So it's finite dimensional systems evolution systems. They happen to be Hamiltonian, but for us now it's a dynamical system or vector field, because you can think about the right-hand side of the equation as a definition of a vector field. It's a dynamical system on a finite dimensional space. 1 plus 1 is infinite dimensional system defined on a space of function of one variable. So this is KdV. The space is a space of function of one variable called x. And we consider its dynamics in T. So this is the equation describing the evolution of function of one variable with time. So sine Gordon, nonlinear Schrödinger, they are all 1 plus 1 systems. Two plus 1 is just saying this is the dynamical system on a space of functions of two variables. So here u, x, y, so in a space of function of two variables, you have evolution, dynamical system. So this is the famous Kadamtsov-Petriashvili equation. And another one, the equation written on a collection of fields, depending on T and X. So here there is one discrete variable and one space variable. And a space of functions is semi-discrete version. Again, we have a dynamics described by this equation. So it's another example of 2 plus 1 systems. Relatively recently, it became a very hot topic, the study of so-called 0 plus 0. These are systems that are systems with a discrete time. So instead of continuous evolution in T, you have a sequence of maps. And again, there are notions of Hamiltonian maps, discrete time systems, and notion of an integrable system. One of my favorite examples of this system is a so-called Pentagram Network. It's a map defined on a space of polygons. So you have a polygon, and you define a new polygon in this following way. You just take diagonals connecting vertices of not the next after the next vertex. And here, and take a point which is the intersection of these two diagonals. So starting from any convex polygon, you get a new convex polygon. So it's the dynamics on the space of polygons. Now you just consider polygons up to conform projective transformation. And there is a, I don't remember what the name of this theorem in classical projective geometry, that if you start with pentagon, then what you received here, so you start with any pentagon, you draw diagonals, you get a new pentagon. It is the same up to projective transformation. So two polygons are equivalent. But if you start with a polygon with more than 5 vertices, the result would be something different. And it happens that this dynamical system is integrable, and in a certain limit, it converges to another equation, which is Not on the list I put here, but you can easily get it if you just, in the KP equation, if you just erase T term. So it's going to be the equation called, and denote Y by a new time, this equation called Boussinesq. And it's surprisingly the equation for dynamics, discrete dynamics of polygons converges after some proper limit to the just another integrable continuous equation. So we'll start today with definition, what it is, integrable systems, my understanding. Then we'll discuss, not of course today, not the next lecture, but the next step in our plan would be to go over how to solve this equation. That's all, what they are, how you can view all of them, then you want to solve them. An essential part of solution is so-called spectral transform. Because when you have some complicated equation and you want to solving equation means that you need to find a good coordinate in which this equation becomes simpler and you can solve it. So the way how all integrable systems are solved is a special transform of initial coordinates to new ones, and this is called spectral transform. So we'll discuss what is spectral transform. I want to, at the end of the course, be familiar with words that are just populated almost any paper on integrable system. Words like spectral curves, Baker-Heezer function. This is what is going, so technique solving them will be our next stops on the way of this course. I will try at the end of the course to present a perturbation theory of integrable systems. Because of course, integrable equation, there are many of them, more and more integrable structures are discovered in physics and mathematics. But the most interesting part starts when you slightly perturb. So it's still, there are a lot of integrable systems, but still they're exceptional. So the whole physics, theoretical physics, were built around very few integrable equations you can solve, like oscillator. And then the perturbation theory is the most interesting part. So we'll talk about rhythm perturbation theory. And almost there is no hope that I will be able to cover in this course applications. So this application includes geometry of modular space of curves, topological quantum field theories, solutions of supersymmetric gauge theories, conformal maps. I can continue. Some of them I will be able to touch. I would like to say a few words about different views on the theory of integrable systems. You see, the theory of integrable systems, the theory of Soliton equations, started with an attempt to solve some equations in a wave type systems, like Carteret-de Vries equation describes waves on a shallow water. And it was interesting to understand how the solution to describe them, to solve Cauchy problem. At the end of 90s of the previous century, it was discovered, but special solutions of this equation describe intersection, for example, intersection numbers on the modular space of curves. It becomes, from that moment, the theory of integrable systems moves slightly its focus from the solving equation in some explicit function to a study of some formal solutions to this equation written, because it turns out that some solutions to this equation, the coefficients of the expansion are some important characteristics in enumerative geometry. They count some invariance in Witten-Seiberg theory, Donaldson. So a lot of answers for problems in enumerative geometry are given in terms of some generating series, and generating series can be proven satisfies one or other equation, and this fact by itself gives a very powerful tool to compute recurrently. You can compute now all these numbers without any problem. And in this form, physics goes somehow aside. And nowadays, when people talking about solutions of this equation, they are thinking in terms of some formal series, not real solutions to some real physical equation. For me, mostly, I would prefer staying in the framework of the old part. So there is some physics, and we want to solve the equation. But still, I will present something what is related to the theory of enumerative geometry and what is actually important for that from the point of view of integrable systems. So what I expect, so some initial level in algebraic geometry, not very advanced, not a language of schemes, but rather classical algebraic geometry of algebraic curves. So it's algebraic geometry of Poincaré time, end of 19th century. Most of needed material from this algebraic geometry, I will explain, I will give some introductory crash course on the theory of theta function if needed, but mostly because my goal is just to present some view on integrable systems. I would like to stay in the framework of linear algebra. You don't need high math to explain what a spectral transform is. But this would be very helpful if you know enough classical algebraic geometry and good understanding of different programming theory, because all equations we're talking about are completely integrable systems or infinite dimensional analogs of notion of completely integrable systems. So good touch of the Hamiltonian theory would be very helpful. Okay, so By the way, probably I will change the pace of my course and the level of going deep or on staying surface of algebraic geometry, depending on the level of students. I still have no very good understanding of my audience, and being on Zoom is not very helpful in that respect, but okay, we'll see. So when I gave a course at Columbia ages back in March, I was giving a regular course. During the first meeting, I put a part of the class on the pre-written screen, like I did it right now. And then I start writing on the notebook here, like I do on a blackboard. At the end of the class, I ask what students prefer, what type. Should I just pre-record the lecture, put notes on the screen and move them back and forth? Or they prefer me to write as I say? So the answer was they prefer just live type presentation, so writing on the quasi blackboard. I don't know what you prefer. I can do both, but can we make a short vote? What you prefer? Just to look at pre-written screen or just blackboard style presentation? There is no reaction. Okay. Probably because you haven't seen the second. Any questions right now? No. Okay. So let me just okay. So what unifies all the equations I named or wrote before? Is there a definition, as I said, of what is integrable soliton equation? Anyone working probably has its own answer. My answer to this question is the following. So let me just give you a quasi, it's not a definition, but it's a quasi definition. Soliton equation. By soliton equation, this is the same as, it's another name for integrable systems. It is the same as compatibility condition. Of overdetermined system of linear problems. So this is a definition, if you call it a definition. Let me just fill this very informal way of thinking about systems by examples. Maybe at the end of the examples, you will understand what I mean. One of the first examples is the most widely used example of this compatibility condition is Lux equation. Lux equation. So what it means? Suppose you have two linear equations, L psi equals zero, and D equals zero, or that's E psi. So this is equation. L is a linear operator. E is a scalar, so it's equation on eigenfunction of some linear operator. And you have the second equation, dt minus A. A is again some linear operator. Psi equals zero. So we have a system of two equations. They may be matrix equation, functional equation, doesn't matter. So it's two equations on one function. And compatibility condition, so the condition that this overdetermined system, because it's overdetermined two equations on one function. Compatibility puts some equation on the linear operators. That implies that dt minus A commutator with L. So you apply operator dt to the first line, you multiply from the left the right hand side, subtract, you get zero. So the commutator of two operators applied to psi is zero. If there are enough, today I'll prefer not to be very rigid in definition. I'm not specifying here. Later that will be clear. Enough psi, so enough common solution to this linear system. Psi solving the system then that means just the equation dt minus A commutator of these two operators must vanish, or that is equivalent to the equation L dot the derivative of operator L with respect to t equals commutator A of L. So this is equation on the space of operators.
Я прошу прощения, а Е это константа, да?
Е это скаляр, да, констант.
Спасибо.
Okay. So in that case, we see We're not just discussing why having one nonlinear equation replaced by another one is very helpful in solving. Let's forget about it. Right now, I want to explain what is the meaning of compatibility condition. The compatibility of Lux equation is just one particular example of this. We'll see later many other examples. All of them share the same feature. It's an overdetermined system of linear problems and compatibility condition on these problems. So conditions that constrain that there are solutions to this overdetermined. Put certain constraint equations on initial operators. And Lux equation is one example of this. You will see many more others. Now let's see examples of this Lux representation. Example. Once again, mostly when I will give example, we'll talk about L being a finite dimensional operator, depending on spectral parameters. Forget about it for a second. But it can be differential operator in two variables, but mostly here. Let's start with a simple example. And it's because it is related to this Krichever equation, the equation from which the theory of integrable systems started. So suppose L is the differential operator dx squared plus u of x t. So it's a Sturm-Liouville Schrödinger one-dimensional operator whose potential depends on t. This is L here, in this example. A is another differential operator in x, dx cube minus 3 over, okay, no. I just take it to be any differential operator in x. V dx plus w. V is a function of x and t also, and w is a function of x and t. Let's see what is the Lux equation in this case. So what is L dot? Okay. So what's the derivative of this operator? This operator acts on a space of functions of one variable. So what is L dot? May I ask anyone give an answer? I just hate to speak with a computer or with an equation.
Ну, первое слагаемое не зависит от t, правильно? Мы же по t дифференцируем. Что оно уходит, у нас остается только вот это u от xt, и от него производная.
U dot. Okay, correct. But U is not, you think about U, not a function. It's an operator acting on a space of functions. So U dot as an operator. So what is its action on F? F is a function. It's a new function. F is sent to U dot F, multiplication by a function. So it's a scalar, if you wish, operator acting on a function. Okay. Now let's compute what is the commutator minus dx squared plus u with dx cube plus v dx plus w. In order to compute commutator, Okay. Another question. Because might be everyone here in the classroom, so-called, made such an exercise. Should I compute the commutator, or you can do it by yourself?
I can do it.
You can. Who else can do it? Who?
I can do it in some time.
Okay, it's not hard. And I'm not going to do such kind of computation in future. I will leave them as an exercise, but for the first time, let's do it right now, just to see. Because computing commutator is just a simple algebra and follows from the, so functions, multiplication by function, commutator u with d, let me, for brevity, to write d just as d is the same as dx. So the commutator is u, the derivative in it, that's all. So if you know this commutator relation, then you just formally compute this commutator. Let's do it. So the commutator of the first term with dx, they commute. With v dx, it becomes 2vx dx square. You just apply Leibniz rule to this term, plus vxx dx. This is the result of commutator of dx with v dx. And I should put negative sign here because there is negative dx squared there. Okay. So the commutator of the next term, u with the third power of dx, would be just negative 3ux d squared minus 3u, just binomial coefficient, xx d, minus uxxx. So this is the commutator of u with the first term. Commuting u with the other one is going to be minus v ux. That's all. And that's it. So this is the result of I forget the commutator of dx with w. It should be minus 2wx d minus wxx. If I missed some other terms, okay, hope not. Okay, so, and that should be equal to an operator, which is multiplication by function. So this should be equal to u dot. So this is the equality of two operators. So it means that it contains several equations on function, because if these two operators equal to each other, that means that on the left-hand side, there is no second derivative in x. So that means that minus 2vx should be equal to minus, should be equal to, so 2x, 2vx, 2vx plus 3ux equals 0. Okay, this is canceling the coefficient in front of dx squared. That allows you to express v as a function of u, 3 over 2u plus a constant of integration. Let's set it 0, it's because it's actually, you get a family of equations that can be easily transformed into each other, parameterized by this constant c. So let's put c equal to 0. This is one choice of the solution. Okay, so the vanishing of the coefficient in front of dx means that vxx plus 3uxx plus 2wx equals 0. So this, that, and that terms. So that gives you the equation v equals negative, so negative 3 over 2uxx plus 3uxx equals 2wx plus 2wx equals 0. I use the expression for v we already found. So that tells us that w equals minus 3 over 4 ux plus another constant, which I also set 0. Okay, so we've ended up with the equation u dot equals, oh, let's collect, minus u x x minus u x x minus 3 over 2 u ux. This is this term. Why nobody corrected me? There is no minus here. It's also
You actually have minus before u dot because you changed the order of operators and commutators.
yes, that's true. That's true. But what? Okay, and here is plus 3 over 4 uxxx. This is the expression we get from wxx. So what it is u dot equals 3 over 2 ux minus 1/4 of uxxx. And this is up to change of signs. U is the KdV equation. Actually, in this equation, in KdV equation, particular values of coefficients are not so important. You just, there is degrees of freedom. You can multiply u by a constant, you can scale by a constant x and t. So actually, using this transformation, you can make any coefficient. Just this particular choice just for convenience. Okay, so this is the Lux representation for KdV equation. So don't ask me at this moment why it's so nice to replace one nonlinear equation, I mean KdV, by some other nonlinear equation given in terms of operator. But it's crucial, and we will see how, because we are going to apply some transform for linear operators that will eventually solve the initial equation. So this is just one example. As I said, I'm not going to do this boring computation. They're just straightforward. You compute commutator, you get something. What is important, what I just want to stress for you, is that the Lux equation is an equation on a certain operators. Okay, let me just give you a list of examples. So KdV, d, L is dx squared plus u of x. This is the operator. This is one. For nonlinear Schrödinger, the equation I wrote before, L is, now L is a differential operator, but with matrix coefficients. It's 1, 0, 0, minus 1, dx, plus 0, psi, bar, plus minus 0. This is L. I'm not, okay, I can write, but I prefer not to write. But I'm not going to compute the exact form of commutator relation. But I is, it is A is I, 1, 0, 0, negative 1, dx squared plus 1/2 0 on psi plus minus psi 0 dx plus dx 0 psi plus minus psi bar 0. So this is operator containing the second and the first derivatives plus minus psi squared 0 plus minus plus psi 0. So if you sit and compute Lux representation, Lux equation for this choice of L and D, you will get that the Lux equation for this choice of operator is equivalent to the equation psi t equals psi x plus minus epsilon psi squared psi. This is not an initial equation. It's just straightforward computation, nothing more. I put plus minus signs here because algebraically these two problems are the same. Physics nature is very different, and the way how solutions of this system behave also very different. One called focusing and defocusing nonlinear Schrodinger equation. Again, this is out of the detailed study of particular solution, particular equation is out of framework scope of this class. And just at this moment, I just want you to remember that. So what I want you to remember? The certain nonlinear equation can be written in the Lux form for proper choice of linear operators. And that can be very different. It can be, as I said, the Sturm-Liouville operator, the Dirac type operator here in the second example. It can be difference operator. For example, what was so the fourth on our list was non-todalated. So it is corresponds to the compatibility condition where L is difference operator n plus 1 plus Vn psi n plus Cn psi n minus 1 equals I psi n. This is L psi equals E psi. This is the discrete form of this equation. And the second equation, very simple, dt psi n equals Cn psi n minus 1. So again, there are two equations on one function of discrete variable psi. And if you write the compatibility condition, you will get two equations. So parameterize C here in the form xn minus 1 minus xn and Vn as xn dot. Then compatibility Lux equation will lead you to the equation xn two dots equals exn minus 1 minus xn minus exn minus xn plus 1. I invite you to do a couple of times this kind of computation. So how to get compatibility condition for these two systems. You differentiate first the first line, you multiply by E the second line, subtract, and see what you get. You get the equation of motion of the todalated. Maybe later, I don't want to spend additional time. I will give you the explicit form of Lux operators for remaining equations in the list I gave at the beginning. So all of them, almost all of them, except Sine-Gordon, can be written in Lux form. For Sine-Gordon, use a slightly different version of it, which is called zero curvature representation. Let's forget for a second about this example. The nature is the same. So now I want to make a dictionary. So what is the subject of our course? What is the subject of a theory of integrable systems? Okay, so as I said, system, dynamical system, is some vector field on a certain space. So this space, usually in Hamiltonian mechanics, is called phase space. So our dynamics is evolution on a space. So what is phase space? Of an integrable system. So the phase space is the space of operators. I want to stress this, depending on a spectral parameter. Okay, I put in brackets this because it's crucial, and I will spend the rest of the time trying to explain the meaning of it. So the pictorial, so I would prefer to think about phase space. It's a space of operators, L. And this is, for me, operator is always a kind of square because it's useful to think of. It's a matrix, because for finite dimensional operator, you can think about it as a matrix. So this is our space, and so in all examples, in all examples I know, you always can represent your evolution system in the form of the vector field on the space of operators. So the phase space, that's why, for me, okay, the KdV equation, you can think about as equation on a space of function. But it's very useful to keep in mind that also that the function u of x is actually a coordinate on a space, a fine space, of linear operators. So I will always identify the space of our system, the phase space of our system, with the space of operators. They might be different. Choosing different spaces of operators, you will arrive at different integrable systems. But the common, so like in the case of Hamiltonian mechanics, whatever its system, the Hamiltonian system is, it's a dynamical system on a manifold called phase space. We will call, for us during this course, this phase space would be linear, a space of some linear operators. Okay, so this is one example. You have sequence of points on the line. It can be made finite by saying that this satisfies some periodic condition plus a constant. Or you put this xm on a circle. Again, this is one way of representing, it's just coordinate, but for me, this is the same as the space of difference Schrödinger operator. So psi n plus 1 plus vn psi n. So the action of operator L on psi is a vector with psi n are coordinates of this vector. So a new coordinate is computed by this expression Cn psi n plus 1. So, and Cn is E xn minus 1 minus xn, and V is xn pn, or xn dot. So again, the phase space of this total lattice system is a space of operators. I insist that you always see the space of certain operators behind every integrable system. So we'll talk about integrable systems as dynamical systems on a space of operators. Now, a basic example. There actually, the whole theory about integrable systems, as I said, my goal is to present general features, structures behind integrability of certain systems. One of them is that they are all systems on a space of operators. And two basic examples would be just KDV or Cadence of Pitviashvili, two-dimensional product lattice. And also another example, basic example, finite dimensional. So example. So if L, so consider this space of just matrices depending on a complex parameter, and moreover, matrices being rational functions of Z. So L put U and Z minus Zi. So it's a finite dimensional linear operator or matrix depending on Z. Z is an external parameter, and that is Z, the spectral parameter. Next time we'll start talking about why it's so important to have spectral parameter. So again, what is this space? This space is U naught I from 1 to M. So this is a space of parameters. Zi, M, number of poles, and each Ui is just a matrix. Of rank R with real or complex supposes. Again, it doesn't matter. Again, so on one hand, we have a finite dimensional space whose coordinates with M and Z are fixed, is a collection of matrices. It's a nice finite dimensional space. But I want to think about this collection, not just in terms of collection of matrices, but as an object which is a linear operator, depending on Z. Another example, so the presence of this external scalar parameter would be crucial for the rest of, it's crucial for the nature of integrable systems. Let's consider a little bit in more detail the previous example. So L is minus dx squared plus u of x. So this is linear operator, as we saw some Lux equations for this L leads to KDV equation. And on first glance, there is no spectral parameter in this operator. So you still can draw pictorially. This is SL, some operator. Question: where is a spectral parameter. Okay, the answer is actually because this symbol in the some hidden form contains this contains the spectral parameter because let me just because infinity in infinite dimensional operator allows to hide some spectral parameter. Okay, suppose U is periodic. Then L, the differential Sturm-Liouville operator. Then L defines, okay, it's operator on a space of function. So, but it can be restricted. L can be restricted to the space of functions such that f of x plus 1 equals z f of x. So actually, that actually not a function. They're a section of some bundle, line bundle on a circle. So if f satisfies this monodromy relation, then L applied to f also satisfies the same equation because z is a scalar. That's why L restricted on a space of function f of x plus 1 equals z f of x. This is this space. Becomes a linear operator depending on z. So the differential symbol as it is written, dx squared plus u. In fact, it's a family of operators acting depending on z. Who can suggest a way to write matrix elements of this operator? What is the basis in the space of function with a prescribed monodromy property? Suppose z equals 1. What is the basis of this operator? What is the basis in the space of periodic functions? Everyone knows, and everyone.
Sine and cosine, I guess, or exponents.
Sine or cosine or just exponential. So you can really write this action of Schrödinger operator in this basis in the form of infinite matrix. In the same way, you can choose just a simple exercise, write a basis in the space of function with z not being 1. Then again, you get some matrix. The explicit form of this matrix is not essential. The purpose of our discussion is actually to discuss that actually the case of KdV equation for any differential operator falls into the framework I put. So we consider space of linear operators depending on a spectral parameter. on some external variable. And that would be crucial for all our further consideration. Okay, so probably it's a good point to stop for today. The summary of what we discussed is as follows. There are a bunch of integrable equations for some unknown reason interesting for physics and mathematics. This can be represented as a compatibility condition of some linear problem. So for each system we're talking about, we can associate a space of certain operators depending on a spectral parameter. This is the subject we are going to study during this course. And next time we start with defining a vector field on the space of operators without using, for time being, the language of Hamiltonian mechanics. This language is replaced by the language of Lux equations. So Lux equations are equations can be seen as a way to define a vector field on a space of operators. Okay, questions?
I have a question about literature, like what books can be useful?
The book, the most, I'll put it, so the book most relevant and close to the line of our thinking here, it's a book called Dynamical System for Integrable Systems. It's a book written by Novikov, De Bruyne, and myself. It will be helpful. Unfortunately, it's strictly textbook for this course. It doesn't exist. Maybe at the end it will appear. The good starting point is a book of Novikov, De Bruyne, and myself. I'll put a link for the PDF file of this book later. Questions?
Вот у меня вопрос, если можно. Я не очень понял мотивацию вот этого уравнения Лакса. Уже изначально у нас было уравнение на пси, правильно? И потом мы его переписали, то есть у нас было задано какое-то L и задано А. И мы хотели найти, насколько я понимаю, решить систему из двух уравнений на пси. А потом мы ее переписали как уравнение на L.
Мы не хотели решить уравнение на пси. Просто условие, что такое решение существует, это условие на коэффициент на L и А.
Я понял, да. Но...
Поэтому, значит, утверждение, что условие совместности это какое-то уравнение на операторы. Правильно? И утверждение, что именно это уравнение на коэффициенты этого оператора эквивалентно некому исходному уравнению, с которым мы стартовали.
Существованию решения у исходного уравнения.
Что?
Эквивалентно существованию решения у исходного уравнения.
Ну, просто это тождественно. Если U от X t решает КДВ, то выполнено уравнение Лакса. Если уравнение Лакса выполнено, то U удовлетворяет коэффициент этого L-оператора, удовлетворяет уравнение Картевега. Просто то вычисление, которое мы сделали, оно показывает, что вот то вычисление занудное, которое я делал, оно говорит, что это уравнение выполнено тогда и только тогда, когда выполнено уравнение Лакса. Это эквивалентность. Просто я пытался объяснить, это существенно для будущего. Я пытался объяснить, что уравнение Лакса возникает как условие существования пси. Сейчас мы не очень интересуемся самими пси, они потом нам понадобятся. Но просто это условие на L. Да? И совершенно непонятно, какая радость от того, что мы заменили одно нелинейное уравнение Картевега на другое. Ну, казалось бы, проделали какую-то алгебраическую процедуру. Да? Но оказывается, это ключевое. Если вы можете представить вашу нелинейную систему как в той, как уравнение Лакса, уравнение нулевой кривизны, уравнение L-B тройки, есть много, неважно, в неком определенном виде, то тогда, оказывается, вот вы замечательным образом можете решить исходное уравнение. Пока мы не обсуждали, как это помогает. Пока целью сегодня было сказать следующее. Есть масса уравнений, выглядящие по-разному. Некоторые очень страшно выглядят, некоторые еще хуже. Все они, о них можно думать, как некоторые динамические системы, векторные поля на пространстве операторов. Я вот вам привел два примера таких операторов. Пока, ну, в случае Криза я даже написал, как писать векторное поле. Да? Для другого конечномерного примера я не писал. Не напишу. Значит, вот, если вы хотите думать вообще о интегрируемых системах, не думайте, глядя на вот эти строчки. Вот одно уравнение, второе, третье. Эти уравнения 50, 60, ну там есть книжки, в которых они все содержатся. Нет. А вот что общего в них? А общее в них следующее. Есть пространство операторов разных, в которых есть возможность определить некоторое векторное поле. И оказывается, вот эти уравнения можно решить, потому что это пространство операторов. Понимаете, когда пространство, казалось бы, когда вы думаете про функцию U от x, ну, функцию U от x. Как только вы ее смотрите как на просто некую координату на пространстве операторов Штурма-Леувиля, с оператором уже много связано. Можно писать задачу на собственное значение, еще что-то. Когда вы пишете просто U, этого не видно. Когда вы его смотрите в комбинации dx в квадрате плюс U, это уже нечто. И вот я призываю думать все время об этих интегрированных системах, как некоторые системы на фазовом пространстве, которые мы отождествляем пространством операторов. Я хочу произвести язык такой же степени универсальности, как язык гамильтоновой механики. В языке гамильтоновой механики у вас, ну, в каждом примере своя многообразие, но вообще-то есть общее. Есть многообразие и симплектическая форма на них. Да? Вот все, что объединяет все гамильтоновые системы. Я хочу предложить такую же картинку для всех класс интегрируемых систем. Вот что заменяет понятие симплектического многообразия. Вот, просто пространство. Так полезно они будут.
Просто чтобы понимать, полосонова структура на этом пространстве берется из двойственного, да?
Ну, еще здесь никакого нет, во-первых, формы, здесь мы ничего не определили. правильно? Вы знаете, это будет следующий этап в нашем разговоре. Значительная часть того, что нужно для того, чтобы решить уравнение, эти лаксы, вообще не требует гамильтоновой механики, ничего не надо. Вот можно решить и все. Мы с вами решим какие-то уравнения. Ну просто, решил. Но вместе с тем полезно понимать связь этого механизма с гамильтоновой механикой. Значит, есть способ, оказывается, на пространстве операторов существует универсальная два форма. И оказывается, что все уравнения, заданные уравнениями Лакса, они автоматически, я не говорю, что они гамильтоновы по отношению к этой форме, потому что эта форма может быть и вырожденной, но уж заведомо всегда верно другое, что контракция векторного поля с этой два формы есть градиент чего-то. Поэтому, когда она не вырождена, у нас все становится симплектическим и хорошим.
Просто я имею в виду, что вот для алгебры Ли на ее двойственном пространстве есть вот эта универсальная форма или универсальная полосоновая структура. И здесь мы думаем про пространство операторов как про алгебру Ли. Правильно? Или не нужно так про это думать?
Это очень легко заведет. Вообще про пространство операторов можно думать двумя способами. Как элемент алгебры Ли и как элемент группы Ли. То есть любую матрицу можно интерпретировать как элемент алгебры или группы. Правильно? И это по-разному заставляет. В общем, на самом деле на пространстве операторов я немножко сказал, есть две универсальные формы. Одна возникает, когда вы думаете про эти операторы с точки зрения алгебры Ли, другая с точки зрения группы Ли. И одна приводит к квантовым группам, а другая к линейным. Здесь мы все это увидим. Но, значит, еще раз. Сухой остаток сегодняшнего обсуждения процесса. Фазовое пространство всех систем, с которыми мы будем иметь дело, это пространство линейных операторов. Если вы это усвоили, можете все остальное забыть. Это примеры. Главное summary сегодняшнего — это не обсуждение, это то, что я вам как бы вкладываю. Вот есть пространство операторов. На них мы будем изучать некоторые векторные поля, которые окажутся гамильтоновыми, которые мы попутно попробуем решать. Спасибо. Значит, еще раз, я надеюсь, вы прислали мне свои имена, список. Я пришлю потом ссылку, если кому-то захочется, на Office Hours, которые, значит, по понедельникам с 10 до 11 можно встречаться, обсуждать, если у вас будет ссора. Не будет. Не будет. Хорошо. Все. Вопросы есть еще? Окей. До свидания. Счастливо.
Спасибо.
До свидания.
До свидания.
До свидания.